Hey class, it's Professor Rourke. Okay, so I've had some questions regarding our section in our textbook 2.4, which always is a bit of a doozy because it is dealing with the quote precise definition or formal definition of the limit. And it looks really complicated because they've tossed some Greek letters in there and they have some weird things going on with the deltas and epsilons, but I wanted to hopefully make sure it makes sense of what we're doing here. Okay, so first things first, it says use the formal definition of the limit and the graph of f of x equals the square root of x plus 1 to find a number delta such that if the absolute value of x minus 3 is less than delta, then the absolute value of the square root of x plus 2 minus 2 is less than 0.2. Like, what is that about, right? And again, I know it looks really scary, but I promise you it's actually, you don't really have to do a lot in this problem. And I think that's what kind of throws people off, besides like being able to identify exactly what is given to you and exactly what we need to find out. Okay, because I think that once we have that down, you'll see it's really follows the same pattern all the time. Sometimes it is more difficult to actually get the numbers out. In that case, those are the questions on WebAssign that maybe say use a graphing calculator is recommended. But if um, it doesn't say that, you can still use your graphing calculator, but you don't have to. Okay, there's not anything, we're not really doing anything much here, which I know again sounds wild, but let me explain hopefully a little bit better. Okay, so hopefully using your textbook kind of got some stuff out of this, even though again, I know it sounds very wordy, but I promise you it's really just saying that if we have some function, okay, so here we're going to say our function is the square root of x plus 1. Okay, and sorry, the quantity x plus 1 is all inside the square root. And then it says find a number delta, okay? Sometimes we're used to seeing delta with like a capital triangle. This is just a lowercase delta, but it mostly works the same as what we've seen in life. Sometimes we'll see something that looks like a triangle and X, and that's just saying like delta X with a capital delta Greek letter. But here you typically use lowercase just because. I don't even know why. You could call it anything, okay? Such that if, and this is where again, I know it looks crazy, but it's all just based off of this absolute, the formal definition of limit. It says the absolute value of x minus 3 is less than delta. What this is giving you, again, this is just piece for piece from the formal definition of the limit. Whenever you see x and delta, especially when it's like x minus 3, what they're telling you is a equals 3. Okay, so all that means is that on our limit, we're talking about approaching 3 from the left and the right. Okay, a is 3. So in other words, you could rewrite this, the limit, as x approaches 3. Okay, that's what that tells us, is just seeing again, if we see it as the absolute value of x minus 3 is less than delta, they're telling us there that we're talking about the limit as x approaches 3. Okay, does that make sense? And then if we usually had it written in the normal, like not very complicated, quote, formal, quote, proper, we would see the limit as x approaches 3 of the square root of x plus 1. Okay, so that's all they're giving us in this first piece so far. We know that f of x equals the square root of x plus 1. We have a graph. Nice, thank you. They didn't have to give us a graph, but I tried to do the graph to see if it could hopefully make a little bit more sense. Okay, and then also there's another part though. It says find, again, a number delta such that if the absolute value of x minus 3 is less than delta, then, and then they have the absolute value of x plus 1, square root of x plus 1. Remember, that's just f of x. Okay, minus 2, this is just L. Okay, that is the limit that they're telling us the limit of this is going to be 2. Again, I know it's weird because it's very fancy way of saying this. Okay, so what they're saying, and again, this is all just based off of matching up like piece for piece directly to the formal definition of a limit. Okay, but also it's just the big idea we want to know is that delta is the distance from x and epsilon is the distance from y, the y value of the limit. Okay, so for this problem, again, they're saying this is f of x, this last piece is absolute value, the square root of x plus 1. They're saying that's f of x minus 2. That's the limit. And we can see that on the graph too. Like the y value is at 2, right? And then they're saying epsilon is less than 0.2. Okay, and that's why they have on the graph 2.2 labeled and 1.8 to try to give you like a visual cue of what they're talking about. Okay, so I know it sounds, again, like very complicated, but all it's saying in this, all of these crazy limit laws that we've had to do and all sorts of weird algebra stuff, all of that's sort of put to the side for right now. And it's just saying, okay, what is a limit? Okay, we know we've talked a little bit about limits, right? It's like where the function's approaching from the left and the right, right? However, like how do you prove a limit, right? And actually this section has been come up in the department when we talk a lot because we don't have very many pure math students. We have students who are typically taking this class in order to move forward in engineering or computer science or teaching, a whole variety of things. So this formal definition of a limit is really just kind of like the why behind like where we say what a limit is. Because a lot of times in math, you know, they always need, they like need the practical math, but they also need the theoretical math. This is the theoretical math that goes behind it. Okay, this is what the definition's saying. All it says is that I can always pick an epsilon. So here the epsilon they picked was 0.2. For every epsilon that I pick, I will have a corresponding delta that tells me how close I need to be. Okay, that's all it says. So it's just like, as I move in closer in the y, I'm going to move in closer in the x, which I know doesn't really sound like much, but that's all we're doing. Okay, so I'm going to walk through a similar problem with you from the textbook, but I just want to get you started on part A, because this is what we, and B, really, because we've talked through this. And then again, hopefully I'll work with it through you. What does the problem ask you to find? So we can go back to the problem and read. Every now and then they do say prove. We're not doing any proofs, okay? I'm just going to be asking you to find delta from this section. That's the main idea. So it says find delta such that, and then again, they give you the rest of the information. So they're asking us to find delta, okay? And then it says from what values from the formal definition does this problem provide? Well, they give us quite a lot, right? They say A equals 3, right? They also tell us that L is 2. They also tell us that epsilon is 0.2, right? Those are all of the values they tell us. And then we can even get more things from here, okay? And that's what I'm going to walk you through in the next problem. So what they're really telling us, we can label these a few different things, but if they're saying that the limit, they're telling us everything. We don't have to find the limit. So they're just saying if the limit is 2, that's what they're telling us. Again, that's what this L means. They're saying the limit's 2 and epsilon's 0.2. That means my values that I'm trying to trap y in, if I take 2 and add 0.2, right, the distance from 2 to 0.2 up to 0.2 would be 2.2. Okay, so you can call this, sometimes I just like to label them, this is like my y2. Okay, just to kind of keep track. And then the distance again is epsilon is 0.2. That could go down. You could go the other direction as well, right? So this would be, maybe I can call this y1. I don't know, just because, okay? So all we have to do is find the corresponding x values. So let's see, 1.8. If I look at the graph, that is corresponding to this like first question mark. Let's go ahead and call that x1. Okay, and then this y2, that's corresponding with this other question mark. Let's go and call this x2. And then what I can do, once I find x1 and I find x2, again, they told us already, we're trying to approach the x value of 3. So I just find the distance between those x values I got to 3, and then I pick the smallest one because that's the delta that I'm going to use for this definition. Okay, so again, I know it sounds like a lot, but really it's all about just picking out what the values are and kind of going from there. Okay, so what I'm going to do is I'm going to pull up almost the exact same problem from our textbook. This is in the ebook. This is number 3, so that we can walk through this one together. And that way you can maybe try the one on the checkpoint by yourself. Okay, ideally, right? You know what I'm saying? Okay. So number 3, again, this is just in the examples after the actual textbook that you guys hopefully took notes on. That these 2.4 notes are not due until this Wednesday. So, you know, all right. It says use the graph of f of x equals the square root of x. So super similar, right? Because in the checkpoint, it's just the square root of the quantity x plus 1. Very, very similar, right? So it says f of x equals the square root of x. We have the graph here. That's nice. They didn't have to give us the graph, but they did to try to help keep the thing straight, right? And I make another video. I'm going to send out a video I recorded before when they don't give you the graph and you have to use your graphing calculator to find the values, but it's the same process. Okay, we have to get out these, like the values are rough on the one that I made a video for from 2.5. I'm sorry, 2.4, number 5. Okay, so let's go back. It says use the graph of f of x equals square root of x. That's my function. Okay, to find a number delta. Yeah, yep, that's what I'm looking for. Same question, right? If, and then this is where the formal definition comes into play. Okay, because it's always the absolute value of x minus a. And so hopefully you got that sort of from the textbook. But again, I know there's just a lot going on there, and this is very much in terms of like the pure math vibes, that which I know a lot of us are just like, can we just see where we're going to use this, please? Which I know, I get you. I'm more of an applied math person myself as well. But here we are. Okay, so we're going to go ahead and say, I hope this makes sense. Again, this is just from the textbook. This is the definition. It's the absolute, this a distance from x to a, okay, is less than delta. So what they're telling me here is that a is 4, and they have that on the graph. See? Right? So this is, in other words, this is just the same thing as rewriting it as the limit as x approaches 4 of f of x, which is the square root of x, right? And we could do this. Like we could say, we can just plug in 4 and say like, oh, the square root of 4 is 2. Like I know that, right? Like we could figure that out. But they even say it here in the other part of it. And they say then the square root of x, again, remember, this is the other part of the definition. And the other part of the definition says the absolute value of f of x minus L is less than epsilon. Okay, so again, just to match piece for piece, square root of x is f of x. The limit is 2, which again, we already kind of knew that. Like we could have figured that out without this much too complicated version, but that's okay. We're just showing like why this formal definition works for these problems. Okay, so another way of writing this very complicated formal definition of a limit, we could have just said, and saved a lot of time and heartache, the limit as x approaches 4 of the square root of x equals 2. Okay, but this is like, why, how can we say that, right? And this is how we can say that with this formal definition, which again, a lot of us are never gonna have to look back on again. But for now, we'll just play by the textbook's rules. I really did try to keep it much shorter than what there used to be, like a much heavier focus on this chapter. Okay, so what they're telling us again is that the limit is 2. All right, so L equals 2. Just want to kind of make sure I'm like labeling this graph as much as I can, but I feel like it's going to get a little wild looking. Okay, so L equals 2. That's like what that's what the limit is. That's the y value, right, of this function really is just 2. And A equals 4, right? And then this is the kicker. This is what they are giving us. They're saying epsilon equals 0.4. So that's why on our graph, they have 2 plus 0.4 to give me 2.4, and they have 2 minus 0.4 to give me 1.6. Okay, so what I'm going to do is I'm going to use these two y values, 1.6 and 2.4, to find these corresponding x values. Let's go ahead and call them x1 and x2, and then I'll use those to find delta. And remember, delta is just the distance from each of those two values to 4. Because that's all it's saying. We're just saying the limit as x approaches 4. All right, and then we just have to pick the smaller one. Okay, I know, very wordy, but hopefully once I just show you how to do this, you'll be like, okay, that's not bad. It's the same from all of these problems, just variations of like difficulty solving for things. Okay, so let's go ahead and say again, hopefully this makes sense. Let's go ahead and say y1 equals 1.6. Okay, how can I find the x value that goes along with that? Right? Remember, again, my function that I'm talking about is just the square root of x, right? You can even write y equals the square root of x if you want to. Okay, and then I'm trying to find out the x value when y is 1.6. So how am I going to do that? Well, I could just take 1.6, right, and plug it in for y, and then I can solve for x. Let's go ahead and call this, again, x1, just to kind of keep it straight, because I'm going to do this 2 times, right? And so then what I really have to do here is just square both sides. And I'm going to go ahead and write like x1 equals, all right, I'm just going to square both sides, and we have to square 1.6. Let me get my, okay, so we'll say 1.6 squared is 2.56. Like, okay. So x1 is 2.56. And that kind of like looks like reasonable, right? Like if I, again, go back to my graph, what they have labeled as question marks, right? I know I don't have to keep them as question marks anymore. I can say that this is the one on the left is 2.56. Okay, that would be the corresponding x value to 1.6. And 1.6 was just taking epsilon of 0.4, right? And saying 2 minus 0.4. So all I do is I'm always going to get like two y values out. If I know the limit and I know the epsilon, I can get out the two corresponding x values. Okay, so I got to do this again though for the upper limit here, right? Of 2.4 is the y2, right? Which again was just 2 plus epsilon 0.4, 2.4. Okay, so I'm going to do this again. So instead, this time, remember again, we're just saying like, let's just say y is the square root of x, all right? And this time I'm using 2.4 is the square root of it. I'm gonna go ahead and call it x2. Again, because it's just sort of, you don't have to label it x2, but it's just because sometimes it's nice to be able to keep track. Like, what are we talking about? Okay, so to find the corresponding x value, I'll just square both sides, right? So then I go 2.4 squared. Okay, and it's 5.76. And that's what's going to happen. These are going to be like decimals. These aren't going to be anything, it's not going to be great. Okay, so I'm going to say 5.76. If the epsilon's a decimal, I'm like, can almost bet a lot of money that delta is also going to be like a decimal. Okay, all right, so all I did again so far was just to take those two y values of 2.4 and 1.6, and I found the corresponding x values, right? And then again, you're like, what am I doing here again? The question wants us to says to find a number delta such that this will work. Okay, so then what we do, once we have these values, I'm going to go ahead and clear out this work here because I have it written down, 2.56 and 5.76. Those are the only two things I really need here. I just need to find the distance from the limit that we're approaching, 4. The x value is 4, right? Remember, a is 4. I'm just going to find the distance from 2.56 to 4 and 5.76 to 4. Okay, so we're just talking about distance. You can think about it a few different ways. Like you could say, if you wanted to keep it in terms of like this part here, x minus a, right, is less than delta. Just remember, it's just distance. So distance can never be negative. So that's why it looks fancy, because it's just saying, get that fixed up there. Okay. Because it's just saying the absolute value if you subtract them. So if you wanted to like match it exactly, you could say like our first x value would be 2.56 minus 4, right? Or that's going to get us the same thing as if we just took 4, take away 2.56, right? Right, you know what I'm saying? It would be the same. Okay, so if we subtract them and then take the absolute value, we'll say like negative 1.44. Okay, so it's saying that delta, I keep messing up my delta and having to erase it. That's okay, let's try it again. It's not a normal Greek letter. I don't know which ones we would consider like normal for my hand, but it's a little tricky. Okay, so what this all comes down to is that like one possible option for delta, we'll say delta 1 is 1.44. Okay, that is option 1. Because I also have 5.76, right? So I'm going to take 5.76, take away 4. That's my other option for delta. Ooh, I almost messed up my delta again. I sort of saved it, but not really. Okay, so this one's a little easier because you can be like, okay, 5.76 take away 4, that's 1.76. Okay, so my second option for delta is 1.76. All right, and then the final thing we have to do is just pick out which one would be smallest, because the thing is that if we used the bigger one, okay, so looking at our numbers, we have 1.44 and 1.76. If we said delta is 1.76, actually, if we took 4, take away 1.76 into the left direction, we would end up past our like our area that we're trying to trap. Okay, like 4 minus 1.76 would be outside, would be bigger, farther away than 2.56. So we don't want to do that. Okay, so we always just pick the smallest one, really. Okay, pick the smallest delta that you just found. So, and that would, in that case, we'd have 1.44 would be my smallest delta, because 1.44 is less than 1.76. We'll say 1.44 is less than 1.76. Like, therefore, delta equals 1.44. Okay, and then we can always click to see, like, I'd be like, what's the answer here? 1.44 or any smaller positive number. Well, that's great. Like that doesn't make us feel any better. But they're saying like it could be 1.4, anything less than 1.44 could work for delta. Anything bigger than 1.44 would not work for delta, because then we wouldn't be able to say that we're within 0.4 of the epsilon. Okay, so again, just to recap, don't really do anything in this problem beyond matching up. You're going to find out what a is. That's the talking about what limit is like x approaches a, right? The limit x approaches 4. You're going to find delta. That's the whole name of the game. But then you're also going to say, okay, so whenever they give me this information, like what's f of x, what's L, and what's epsilon. So you take the L and the epsilon to get two possible y values to trap it between. And they're often given to you in a graph like they have here, and also in the checkpoint, they give you the y values. That's like why they're kind of written like that, is that hopefully you'll be like, oh, okay, I don't even have to do that really. Okay, I already have, let me clear this other part off. I know my y2 is 2.2 and I know my y1 is 1.8. Okay, so then we find the quote corresponding x values to go along with that. We were able to do that pretty easy because we were to say 2.4 equals the square root of x, solve for x. 1.6 equals the square root of x, solve for x. And then we find the distance between those possible x values and our a value here, which is 4. And then we pick out which one's smaller. Okay, so I know it does sound like a lot, like I'm not saying like you're not doing anything, but you're not really like doing, like you're not actually finding the limit. The limit is already given to you in this definition. It's just that we then have to kind of work around and be like, okay, this is why it works. So again, I know this section's always a little challenging because it's like, what am I like, why am I doing this? You know, we already are finding limits and now we're going back and saying like why they exist, you know, which is actually kind of like how the history of math usually works. Is like, oh, look at this. This works out really well. Kind of like what we've been doing. Like this is the limit. And then someone's like, well, can you prove that? Because if you can't prove that, then we can't really be saying this. And then so that someone's like, okay, let me go back now and see if I can formally prove this. And there's always a sort of like two sides of mathematics. There's the people who are just like, let's see how it works. I'm not going to question how it works, but it works. So let's just do this. And there's people that are like, but why did that work? I need to see the proof. And this is kind of what we're doing in this section. So again, I hope this was helpful. This was from 2.4. And there was a tricky one that I made a video for that I'm also going to include in this announcement. Looking through this ebook, it corresponds like to question number 8. Okay, I believe, because we have to use our calculators to like be able to solve something like that. I think that's what it was. Like we didn't have that much of an issue when we were trying to solve for x because the function was the square root of x. So we were just able to say like, okay, let's solve for x. Like 2.4 equals the square root of x. I can square both sides. We don't really have that option on these like really ugly ones that we don't really have the ability to solve for other than using technology. Okay, so I'm going to send a video out for that one. Again, this was previously recorded, but it still applies. So again, I hope this was helpful to sort of give you the confidence needed perhaps to solve this last problem on the checkpoint. Remember, checkpoints are graded for accuracy, just so I can kind of give you feedback on how things are going, but you are more than welcome to come see me during office hours or the AACC Tutoring Center for help. I know some of us have a lot going on and busy. And so I actually did find out today that they were able to add on another virtual tutor Sunday mornings. So I'm going to update our homepage with all of the different hours. There's some evenings, sorry, and there is some weekend hours where people can help you. On our checkpoints. I just don't like to go outside because you know every college is different. Every person who learns math is different, and the people at ACC at least know exactly like what the expectations are and how you want to like explain it, right? So that's the main idea for these checkpoints, is just to give you feedback and be able to check in with you before we have to worry about the test or anything like that. So there's typically 2 checkpoints for every section, and I try to get like 1 question of each type from our homework that maybe you could expect to see on the exam. So these, along with the test review, are super helpful to feel prepared for the exam. So there's no surprises there. Okay, thank you, class. Please keep me posted and let me know if you have any questions. I'll be happy to answer them. Thanks.